Hi, everybody. Thank you so much for joining us today. My name is Jennifer McConnell. I'm the product manager here at Protochips. If you're not familiar with Protochips, welcome. Our company focuses on workflow solutions for in-situ transmission electron microscopy research, which means our developments and our offerings include tools that support sample preparation, data collection, and large data set management, and everything in between for nanoscale in-situ research. So ensuring all the gaps of these workflows are filled is what enables us to carry out our company's three main goals, which are to help our researchers scale from bulk to the nanoscale with relevance, to accelerate productivity, and to foster collaboration and discovery. So today we're doing our second installment in our mini series, Go with the Flow. It's all about understanding liquid flow dynamics in our Poseidon AX system. It's our liquid cell for TEM. With such a breadth of applications that are relevant for liquid cell TEM, understanding liquid flow and how it could potentially affect these different experiments is obviously critical during experimental design, but of course also during execution. In particular, electrochemical experiments in Poseidon, well, really in all liquid cell TEM, but have presented their own unique challenge, which are high amounts of gas generation. Many electrochemical experiments, especially for electrocatalyst research, purposefully produce gas at bubbles, and which is something that you're typically trying to avoid in liquid cell experiments TEM due to such restricted speed. But the value of the information to be learned has kept researchers persevering over the years despite the challenges that were presented. So today's speaker is going to discuss this topic in general and how implementing the Protochips new flow management e-chips, which were designed to increase control over flow and bubble movement, have completely changed her workflow. So before I introduce the star of the webinar today, a couple of housekeeping items to cover. Everyone is muted due to the audience size to prevent unintentional interruption. If you have a question for our presenter, please enter it in the questions box on your GoToWebinar panel, and we'll address it at the end of the talk. There'll also be a short survey that pops up at the end, and we greatly appreciate it. It's very helpful for future webinars. There will be a certificate of completion that comes in your email after the webinar if you need one. And I just want to do a quick short plug for our next webinar series as well, which is surrounding bridging the pressure gap, which are gas phase experiments in the TEM using our Atmosphere AX system. There's a link in the chat if you want to go ahead and register for those so that you don't forget about them. Okay, that's enough of me. Without further ado, let me tell you a little bit about our speaker today, and I'm going to hand the mic over to her. So Kasia Bejtka received a bachelor's degree in physics from the University of Technology and Agriculture in Poland, a master's degree in materials physics and nanotechnology from Linköping University in Linköping, Sweden, and a PhD in physics from the University of Strathclyde in Glasgow in the UK. She was then a postdoctoral researcher at the Italian Institute of Technology, working mainly on morphological, structural, and chemical investigation of nanostructured materials for energy applications. Her work included a variety of analytical techniques, including mostly electron and ion microscopy, EDX, and EOS spectroscopy. Since 2021, she's been working at Polyteo and is affiliated with IIT and has been working on development and application of advanced in situ and operando transmission electron microscopy techniques for energy applications. So this includes electrochemical liquid phase TEM for the study of catalysts for energy applications, including the electrochemical conversion of CO2 into high-value organic molecules, and electrical biasing and thermal TEM for the study of microelectronic devices. She's got an impressive publication summary with over 70 publications, over 1,770 citations, and an H-index of 24. I'd like to introduce Dr. Kasia Bejtka. Thank you so much for joining us, Kasia. We're looking forward to your talk, and I'm going to hand the mic over to you. Begin whenever you're ready.
Okay, thank you very much, Jennifer, for your introduction, and thank you for having me here to share with this broad audience our recent results. And good morning, good afternoon, and good evening to everybody who is following us. So I will be speaking about the role of the liquid flow configuration and electrochemical liquid phase TEM in aqueous electrolytes. And this is the no, it's not. This is the outline of my presentation. So I will start with a brief intro to show why we as a group and researchers in general could be interested in electrochemical liquid phase TEM in aqueous electrolytes. Then I will briefly describe the experimental setup, especially to those who don't know it yet, so we are all on the same page. Then I will be speaking about the research challenges in electrochemical liquid phase TEM, as it is important to take in consideration that this cell is very different from the classic cell, where the materials are tested, and we will have some challenges there. I will describe the liquid configuration in this setup, and with this I will pass to the discussion of the influence of the liquid flow configuration on the electrochemistry. And I will show this on the base of the optical microscopy experiments and in-situ TEM experiments. With this, I will pass to the discussion of the results, and I will show the results on the electrodeposition of zinc nanostructures and dynamical evolution of copper-based catalysts for CO2 reduction reaction. And afterwards, I will conclude this presentation. So, sustainable energy future is of interest among the scientific community, especially in the context of the ongoing global energy crisis. And electrochemical technologies for the energy or fuels production are of high interest. And this include, amongst others, water and CO2 electrolysis. Functional materials are used as electrocatalysts. They are required to trigger the reactions involved, and their full understanding can help to optimize them, to increase their performances. And let's say pre-in-situ era, the understanding of the phenomena underpinning the catalyst behavior was based on the characterization, for example, by microscopy, of the as-synthesized catalyst and of the catalyst once it was tested. Then the information was also gained from the electrochemical characterization and product characterization and speculative modeling. But in recent years, the TEM in liquid became possible to the development of the specific TEM holders, and now we can actually study the catalyst during the electrochemical liquid phase, during the electrochemical investigation. So here I show you the electrochemical liquid phase TEM holder and how it is made. So basically we have the miniaturized liquid cell placed in the tip of the holder, and the liquid can be flown through the cell. We have two inlets and one outlet, and we also have the contact paths, which are there for provision of the electrochemical stimulus. So this kind of holder open in principle a whole range of exciting possibilities for fundamental and applied research, allowing imaging and characterization of chemical and physical properties at the nanoscale in liquid environment, while we are providing the electrochemical stimuli. And in operando TEM for catalysis, we can be interested in studying the startup phase of the catalyst materials, and we could be interested in doing this after the activation of the catalyst, and we could also be interested in study the surface reconstruction. And also, it is very interesting to track the dynamical evolution of the catalyst during the operation. So basically, this is a whole range of exciting possibilities. However, it is important to remember that this cell is very different from the classic cell, and there are some research challenges. So here I show you how the classical cell, so the macro scale cell, is made. So we have, in simplified view, we have three electrodes which are immersed in the conductive electrolyte. We have a working electrode on which we will have our catalyst and on which the reactions of interest will take place. Then we have the reference electrode, which is the electrode that is measuring and controlling the potential, and counter electrode, which passes the current which is needed for the working electrode to be kept at the central certain potential. As I said, we place our catalyst at the working electrode, and everything of interest actually happens there at the interface in between catalyst and the electrolyte. And while we are running the reactions and we would want to run the reactions in which we obtain the products of the interest, which can be gas, liquid and gaseous, we will also evolve the gas products, which are the competing products at the counter electrode and at the working electrode. So you have seen that the cell is quite complex, and there are requirements, and in TEM there are requirements for the electron transparency and for the compatibility with the high vacuum of the TEM column. And this will have direct influence on the liquid cell geometry. So as a result, the liquid phase TEM will be different from the macroscopic counterparts. So here I show you how the liquid cell is made. So basically we have a large chip and a small chip that they are faced one in front of the other, and together with gasket they seal the cell and create the miniaturized cell. Both chips, they have spacer incorporated in them, which will define the thickness of the liquid layer on top of the working electrode and in general in the cell. And the electron transparent region is defined by suspended silicon nitride membrane, which is here in the central part. And this is how it looks when we look at the cross section. So we have large chip with its silicon nitride membrane, small chip with its membrane, and the liquid in between those. The electrodes are patterned on the nanos chip, and we have the working electrode in the central part, so it's here, and this is made of platinum or carbon. We have the reference electrode down here, and the counter electrode is here. So, as a result, we see that the miniaturized cell is very different from the macro scale, and therefore the electrochemical response of this cell will be affected by its differences in terms of the electrodes configuration and the effect of the liquid thickness, and also by beam induced effects. And everything will be also influenced by the liquid flow configuration. I will briefly discuss the three first points, and then I will focus on the influence of the liquid flow configuration on the electrochemical liquid phase here. The first, as I said, is the fact that we use the electron beam to probe the material, and we do it in a very small region. And while we probe the material, some of the electrolyte will decompose in the process called radiolysis. The water molecules are broken and they recombine in the series of the steps, and they form many various radicals and species containing hydrogen and oxygen. And at the end of all this, we can have creation of some bubbles, which will possibly then stick in the experiment. This process is being widely studied, and there is a lot of literature about it. And there are also some mitigation strategies. So this process can be reduced by reducing the electron dose during the experiments. We can reduce the temperature of the experiments. We can also incorporate some chemical scavengers, which would reduce the radicals, so that the molecules that produce radicals. And last but not least, we can take care of refreshing the liquid solution at the electrode by flow of the fresh electrolyte. So with this, I want to pass to show you something about the electrodes. So the electrodes are very different in this miniaturized cell in comparison to the macro scale, because they are all patterned at the big chip. So it is a MEMS chip, and it has 3 planar microelectrodes. Working electrode, which is made of sphere, and it is made of platinum or glassy carbon. Glassy carbon is preferred for catalysis, as in the macro experiments, this is what is usually used for dispersed catalysts. Then we have the reference electrode. The reference electrode is made of platinum. It's in here. It's made of platinum, and it will possibly be a source of uncertainty because it is highly sensible to the chemical environment and to the different dissolved gas. And the last electrode, the counter electrode, which is sitting here, is also made of platinum, and it can generate gas, and therefore it can be a source of reductive or oxidative species that might come into the working electrode area and interact with the sample. So in general, this is something that can happen, and in general, in gas evolving reactions, bubbles can be formed on the working electrode and on the counter electrode, and they can cause electrolyte dewetting in these cells and limit the overpotential that can be applied. And here I show you what can happen at the working electrode. This is actually optical microscopy image, and I show you the cell, how it looks when it is fully filled with liquid. This is the working electrode. And when we apply some cyclical parametry to the electrode, it can happen that we form the gas bubbles due to the chemical reactions at the electrode. And if we can we can imagine that this production of the gas will easily saturate the cell above the working electrode. We were actually interested to see what happens in the whole cell. So in order to understand whether the gas products are produced only at working electrode or also at the counter electrode, the experiments were carried inside the Petri dish, like as I showed here, and the big chip was interfaced directly with the potentiostat by contacting it with the big chip pads. So actually we are studying open cell, not the closed cell, and we perform some cyclical experiments in various potential range in order to understand whether the gaseous products were produced in all potential range, and also to investigate whether they are produced at working electrode and counter electrode or both. And we observed that in all experiments there is more or less, but there is production of the gaseous products, and they are observed at both of them. So if you can imagine these big bubbles in the closed cell, where we have a little liquid, so small thickness of the liquid over the electrode in the cell, this is a major problem, the saturation of the gas, because it is easily happening that this miniaturized volume of the cell is immediately saturated with the gas. We can try to mitigate this problem by various strategies. One can be by increasing the spacer and therefore increasing the thickness of the liquid on the within the cell. And another could be also by flowing the electrolyte at faster rates, which we did try. We increased the flow rates from 300 microliters per hour, which is something that is a standard flow rate, till 3000, but obviously we cannot put too much pressure, as we would be afraid to break the membranes inside the TEM. With this, I come to think about what would be the influence of the liquid thickness within this cell, and the two aspects need to be taken into consideration when we are speaking about the thickness of the liquid without this cell, which is the electrochemistry that we want to run, and there the electrolyte is responsible for the ion transport and electrochemical activity. So we actually want to have electrolyte. And from the other side is we want to think about the resolution. And we know that liquid silicon suffers from the reduced resolution because of the electron scattering from the silicon nitride window and also from the liquid layer. We also need to take into consideration the catalyst size, because larger catalysts will require larger spacer and therefore more liquid within the cell. Because obviously, if we have big particles and we place them on the working electrode, once we need the spacer, which is bigger than the catalyst, to don't break the windows once we close this. It was shown in the literature that performing the electrochemical water splitting in situ can generate the gas bubble. And with this, we can reduce the thickness of the liquid at the working electrode, so at the point where we want to perform our investigation. And this means that with this reduced liquid thickness and liquid covering the sample, the acquisition of good resolution images is possible, and it is also possible to perform chemical analysis through EERS and structural analysis to selected area diffraction analysis, which is very different and in contrast to when we are performing the characterization with big thickness of the liquid, where the resolution of the image is very poor, and the chemical or structural characterization is also uninterpretable. Obviously, this situation, this gas bubble generation, needs to be taken with done with care, because we don't want to saturate the cell and the wet electrodes completely. After, when the characterization is performed, the liquid can be flown back to the cell for further experiments. And with this, I come to show some information about the flow. So as you have seen, in electrochemical liquid phase TEM, flow is necessary, and it is necessary for the provision of the fresh electrolyte and for the removal of the products of radiolysis and electrochemical reactions. And actually, the efficient flow could remove the products before they create the bubbles to dump the wet electrodes. And this could happen both in the case when we are speaking about the radiolysis and if we are speaking about the products created by electrochemical reactions. In the liquid phase TEM, the flow must reconcile both imaging and electrochemistry. And we would wish that the flow at the working electrode is not too fast, not to detach the catalyst and not to disturb the imaging and the diffraction, but out of the working electrode, efficient flow rates permit removal of the products at the counter electrode, which is also very important. So efficient flow is very, very important, and the efficiency of the flow will depend on the liquid cell geometry. And in previous Go with the Flow webinar in December, Dr. Stefan Merkels from Mamaguna in Spain was speaking about the mass transport in different liquid phase TEM flow scenarios. And he presented the novel chip design, the novel small chip design, which I showed here. With this chip, this chip differs in geometry in comparison to the standard chip. It has on-chip bypass channel, which you can see here, and this bypass channel goes around the imaging area. So basically, we have this 10 micrometer deep channel within the chip, and the finite element modeling showed that the flow is very efficient, and it is efficiently guided in the channel around the viewing area, and the mass transport, the dominant mass transport mechanism in this on-chip bypass channel is by convection, and in the viewing area where we continue to have the nano-size channel, the replacement of the solution or of the electrolyte is faster than in the conventional cell, and the mass transport mechanism, the dominant mass transport mechanism is by diffusion. So basically, it was shown that the new design permits fast solution replacement in the viewing area, and the hydrodynamic properties parameters of the proposed cell were very much improved. So the flow geometry was very important for those experiments, and we here want to understand if the modified liquid flow configuration of the small chip is beneficial for electrochemical applications. And this is done in this presentation by comparative experiments, where I will show you the results using the standard and the modified small chip. And we want to monitor the situation between the cells. So we want to monitor the bubbles, let's say, on the working electrode and in the cell in general, while we're providing the electrochemical stimulus. And I will show you two experiments. I will show you the in-situ experiments, where the cell is closed with the standard silicon chip, and I will show also the experiments performed under optical microscope with the use of the glass chip. So basically, the big chip was prepared on the glass, all the electrodes, disposition, and everything is the same as in the standard silicon chip. So this is how it looks when we close the cell for the in-situ experiment. So basically, you see the small chip and the big glass chip. The glass chip has all platinum electrodes in this case, and we will investigate what happened in the cell when we close it with the standard or with the modified small chip. You can see from this image here that the counter electrode and the reference electrode are actually aligned with the bypass channel. So where there are present, we actually have quite a lot of electrolyte. So I will show you the results when we apply some electrochemical stimuli at cathodic potentials. And we will investigate the behavior of the whole liquid cell under the electrochemical stimulation. I just want to add that we have studied various flow rates to understand also the influence of the flow rate for this. And these experiments were done in the electrolyte saturated with silk. We are interested in the applications for silk reduction reaction. So as I show, we can access with this glass chip, we can have access to all electrodes. And this is the area which we could have observed if the top chip was made of silicon, so if it was a standard chip. I show you the first experiment where the glass chip is paired with the standard small chip, and we will investigate the behavior of the whole cell under the provision of cyclic voltammetry stimulus. The cyclic voltammetry in the range between 0 and minus 1.2 volt versus platinum, and I will run this video now, and we can observe that there is the formation of the bubble here at the counter electrode at approximately minus 1 volt. And then I will play it again. This bubble is becoming bigger and bigger, and it's not efficiently brought away. We also see the formation of the bubbles in the area of the working electrode, where the bubbles of hydrogen are produced. And we have seen that everything then is like a big gas chamber, and it saturates quite much the cell. We have seen that when the bubble is produced, when we go back with the potential to 0 volt versus platinum, the gas produced is still remaining there for quite a while. It actually takes 10 minutes to completely recover the liquid. Let me show now the same or similar experiment, but done with the modified flow configuration. So glass chip is interfaced with the small modified chip. And here we can see that we can open the potential window more. And this is thanks to the fact that we have more electrolyte where the reference and counter electrode are placed. And the electrolyte, so the electrolyte volume is bigger and the flow is better, which means that there is increased mass transport within the channel and the bubbles can be removed more efficiently. So this is why we can open the potential window more. And we observe that actually the products are removed in much more efficient way. And when the bubbles are formed, they are also brought to the outlet port very easily. We observe the creation of the hydrogen at the working electrode, but it must be pointed out. We cannot see it from this video, but I can say it by words. So it must be noted that when we are at not very much negative potentials, but something like -1.1, -1.2 volts, this improved liquid flow configuration inhibits formation of the gas bubbles in the working electrode area. The bubble is formed when we reach more negative potentials, where the reaction and the gas products are already quite important. But the gas products then are quite easily removed from the working electrode area as well. And this is because we have improved mass transport around the working electrode area and also within the working electrode area. And here I show you the situation. So after the experiments are run, we remain in the standard configuration. We remain for quite a lot of time with the bubbles sitting there, while the gaseous products are efficiently removed from working electrode area and the counter electrode area in the modified cell. So we have the fast recovery of the condition with the cell fully safe liquid in a very short time. So now I want to show you the in-situ experiments. So here we will follow the intensity of the transmitted electrons, which is low when the cell is filled with liquid, because we have high scattering of the electrons in liquid. And it increased rapidly when the gas bubble is formed due to the lower scattering of the electrons. So in the next slides, I will show what's happening on the working electrodes, which is gas carbon. And we are studying the situation where the material is not deposited on the working electrode, so on the working electrode. So here we will study the contribution of the working electrode in the gas production when the silicon large chip is paired with the standard or with the modified small chip. As I said, we will have the situation now with the gassy carbon, and the methods of observation, of assessment of what's happening there are qualitative observation of the bright field TEM image, quantitative or by investigating the transmitted intensity in TEM, and semi-quantitative electrochemistry. So here I show you transmitted intensity acquired during the provision of, so during running the chronoamperometry in one of the cells. So we start with the full cell, and the transmitted intensity in the TEM is low. Now I will show you what's happening. So once the bubble is produced within the cell, the intensity is increasing, and you can observe that there are actually some particles on top of the working electrode. And then you will see some dynamics and passing of the bubble. So actually there is some gas within the cell, and the bubbles and the electrolyte are pushing themselves away. So this is just to show what we are observing in TEM when we are investigating what's happening on the working electrode. So here I will show you what's happening and what is the contribution of the working electrode in gas production when we pair the large silicon chip with standard and modified small chip. So I show you the transmitted intensity curves acquired during the cyclic voltammetry experiments. And here you can see, and I showed you also this to you before, that when we have this abrupt change in transmitted intensity, it means that the electrolyte layer is thinner because there are some gas produced there. So basically, we can see that there is a huge difference in between these two cells. So in the standard cell, when we run the cyclic voltammetry in the range between -1 and 0 volt, the cell actually quickly is filled with the gas, and the transmitted intensity in the TEM is increased, as you can see here. And this is actually happening in all tested cyclic voltammetries when we're opening more and more potential windows. And when we perform this experiment in the modified cell, we don't observe any change in the transmitted intensity in the TEM, and it means that the cell remains always full with the electrolyte. So this is the situation, the CB in the standard configuration, and here I show the CB acquired in the potential range between 0 and 2 volts versus platinum, and we can see that we actually obtain nice predictable cyclic voltammetry curves. And when we perform the chronoamperometry, we observe similar behavior. So when we perform it in the standard configuration, there is the formation of the gas bubbles at the working electrode, and the cell is immediately filled with the gas. With this, I don't want to say that we don't have any electrolyte anymore on the electrode. We actually possibly have some, because we can run the chronoamperometry, but we don't know if it is covering well the working electrode and the catalyst itself. In the modified cell, we observe that the chronoamperometry can be run. The potential of -2 volts versus platinum, we were running it smoothly for 10 minutes, and we know that actually it can be run for even longer times. And these experiments can be carried out with the liquid cell fully filled with the electrolyte for the extended time, as I mentioned. So now I will show you two examples of newly accessible experiments in aqueous electrolyte. First is the electrodeposition of zinc nanostructures, which are of interest of energy storage application. And the second is the dynamic evolution of copper-based catalyst for CO2 reaction application. So I will start with electrodeposition of zinc nanostructures. So when we want to perform the zinc nanostructure electrodeposition, we perform the electrodeposition at working electrode, but we also have the competing production of competing products, which is evolution of hydrogen and production of the oxygen on the counter electrode. And this was actually tried and studied by Sasaki and his co-workers. So they did the electrodeposition of these nanostructures in situ with the same setup as we have, so Poseidon select of prototypes. And they showed that with the standard configuration, so with the standard small chip, they are not, it is not possible to deposit this nanostructure. So basically here I show you the working electrode and the liquid surrounding it. And when the current is applied to perform the electrodeposition, the cell immediately is filled with the gas. So with the conventional experimental setup, it was impossible to perform the electrodeposition due to the gas saturation of the liquid cell, and that was mainly oxygen produced at the counter electrode. They wanted to study the zinc electrodeposition, and to be able to do this, they deposited the zinc layer on the counter electrode to inhibit the production of the gas during the electrodeposition. So they then were able to perform and study the electrodeposition process, which was of their interest. However, with addition of the extra technological step, which was prepared ad hoc for this experiment. So we want that if having this improved liquid flow configuration can help and make it possible to perform this experiment without incorporation of this technological step. And this is what actually I will show now. And first, I show you here the experiment which was repeated on the basis of the Sasaki and co-workers experiment. So we ran the chronopotentiometry at the current density of 20 milliamps per centimeter square in the same electrolyte, and the cell has all 3 electrodes made of platinum. So when we close the standards, the cell with the standard slot sheet, we actually observe the same what was observed by Sasaki and co-workers. So immediately after the current is provided, the cell, actually this is not anymore liquid area, the cell is filled with the gaseous products. And when we use the modified, so the improved flow configuration cell, and apply this chronoamperometry, we observe growth nucleation and growth of zinc nanostructure, so that the electrodeposition was performed. And we have run this for a little bit longer times because we have run for 120 seconds and added these 2 initial steps to go to the current of interest in a slow manner. And we observed that actually for all this time, the cell stayed filled of liquid, and the gas production, which possibly was still competing reaction there, was not disturbed in the deposition. The next example, which I want to show, is the dynamical evolution of the catalyst for CO2 reduction reaction. So we are interested in the framework of the project to study the copper-based electrocatalyst for CO2 reduction to produce the carbon monoxide. And this copper-based catalyst is actually a catalyst in the form of the cubes with TEM-based shell, which should enhance its stability and Faraday efficiency. So before we were able to perform the in-situ, because we were not having the improved modified liquid cell configuration, we did test this catalyst before and after electrocatalysis, and we observed that part of the material changed in the morphology, and actually we observed also some structural changes. And we observed also that some of the material remain not very much affected. And this leaves a lot of open questions in regard to what actually happens and why part of the material changes and part not. And here I show you the dynamical evolution of the catalyst for CO2 reduction reaction. Actually, I show you the frames taken at the have to use to be able to follow some particular tubes. So basically, we have run some electrochemical experiments and the chronopotentiometry at the current density of 2 milliampere. And we were able to study this catalyst at the potential which were comparable with ex-situ experiments. And we observed that some of the tubes, as this one, for example, remain more or less unchanged during this very long experiment. Some disappear, so dissolve quite much during these experiments, and some undergo some changes, so it's not completely disappeared, but it's not remaining unaffected. But the very important message from this is that the use of this flow management chip permits us to study the catalyst under relevant electrochemical stimulation, which was not possible with the standard configuration. This, together with some post-operando characterization, so we did some EDX mapping of the chemical composition, gives us some preliminary information. So basically, it suggests that thin dioxide particles enhance the stability of the tubes by protecting them from the dissolution, precipitation phenomena in the solution. As we can see, from this EDX, where the tube was very much dissolved or so affected, there is not much thin there, and the tube that is unaffected is still quite much covered by thin dioxide particles. So this is our I showed you the results, very preliminary results, and we will be running some more of those experiments and investigate this further. So with this, I come to the conclusion. So I hope I have convinced you that the modified and optimized flow configuration is very interesting. It helps us or helps the electrolyte to be flown more efficiently through the cell. And in this configuration, in which we have higher electrolyte volume at the counter electrode, and this improves the removal of gaseous products from the counter electron region. And in the viewing area, the diffusive mass transport is favored, resulting in improved removal of gaseous and liquid products from the working electrode, so from the catalyst at the working electrode. I showed you that electrochemical experiments can be carried out with the liquid cell fully filled with the electrolyte in extended range of the experimental conditions, so down to the -2.2 volts versus platinum, which is more or less -1.4 versus reversible hydrogen electrode. So thanks to this new design concept for liquid flow cell, it is now possible to work in the range of the potentials which before were not accessible, and we are quite sure that electrolyte is actually covered with the catalyst in these experiments. So I have shown you that it is now possible to electrodeposit zinc without incorporation and further technological steps and modification to the cell. And I have shown you with these preliminary experiments that we can follow the dynamical evolution of copper-based catalysts, which confirms all the above points. And we have seen that thin dioxide particles enhance the stability of the tubes by protecting them from dissolution and precipitation phenomena in the solution. And with this, I want to pass to my last slides, which are acknowledgments. I want to say thank you to everybody that contributed to this project, and also to the family. And thank you for your attention.
Kasia, thank you so much. That was a wonderful talk, and you have accomplished a lot of work in a relatively short period of time. That is amazing. So thank you so much for putting all that together for us. We'd like to go over some questions and answers now. And if you have some questions, now is a great time to submit them in the questions box for Kasia, and I'll read them out to her and she can answer. We do have some at the moment. I just want to throw a small plug in there. Those modified chips that Kasia has been talking about, we have deemed them our flow management chips, and they are available if you have a Poseidon system to purchase at this point. And if you have any questions about it, you can send an email to orders@protochips.com and we'll help you find all the right information to figure out what you need. Okay, madam, let me turn to the questions here. So the first one says, thank you for the nice presentation. Have you tried higher potentials such as 5 volts? And do you think the modified small chips are suitable for small gas bubble formation? Thank you.
So we did not try such a negative voltages, so I'm not sure what will happen there. And surely it will also depend on the electrolyte. So in this presentation, I was speaking about the bubbles produced in aqueous electrolyte. So maybe if you are studying the different electrolytes, the situation will not be as dramatic in terms of the production of the bubbles as it's here. But no, we did not try it.
Okay, thank you. We've got a couple of questions related to flow rates. So the first one is, thank you for this very nice talk. How much is the flow rate that can be supported by the modified E-chip if we consider that it will not affect the electrochemical measurements and the nanoparticles? So I guess what is the maximum flow rate that you've seen effective with the modified chips?
So we did try the flow rates up to 2,500 microliters per hour. Possibly we did try something bigger as well, but we did not observe big improvements when we passed from 1,200 to higher flow rates. So there was some improvement in the standard cell actually when we did try it, but in the modified cell we did not see improvement. So we don't see the point of going to higher flow. So this flow 1,200 is actually very effective already.
Perfect. And just for comparison, the other question was related sort of like this. For the standard configuration, what flow rates were you typically using there, and how is, to compare to what's been optimized now for the modified chips?
So for standard configuration, usually we did use 300 microliters per hour, which is something that Protochips actually is suggesting. We did try higher flows, so we did try to go to 1,200 and even 1,500, but there was not much improvement observed there. There was some improvement observed when we were increasing the thickness of the spacer, but obviously this is something that we were not really wanting to do because then there is a lot of electrolyte and this disturbs imaging, but flow was not very advantageous for this.
Okay, yeah, that makes sense. Did you see a substantial improvement in mitigating de-wetting when using a gas-saturated electrolyte like with CO2 with the new flow chip? And if so, how much longer were you able to maintain a fully hydrated cell as compared to the standard configuration?
So in standard configuration, we were not able to perform the experiments at very negative potentials. And if I'm speaking about very negative, I'm actually thinking about something more negative than minus 1.6 volts. In the modified configuration, we were able to perform without the wetting of the electrode, the experiments, until minus 2.2, minus 2.4 volts versus platinum. We were able to produce the bubbles on demand when we wanted to do some more high resolution imaging, and then we were producing the bubbles with more negative potential. But at the potentials of interest or the potentials that I have shown you, we were able to keep the cell fully filled of liquid or at most of the times.
Great, and that was even with using a gas-saturated electrolyte? Like, did you?
Yes, yes. All the experiments that I have shown, like the comparison experiments, can you see? So those experiments, they were all performed in the electrolyte saturated with CO2.
Perfect. Wonderful. And so you touched on something that there was another question about too. The question was, is it more difficult now with the modified chips to intentionally generate a bubble and de-wet the cell if you want to do like higher resolution or diffraction or something like that?
So with this modified cell, we actually need to go to quite negative potentials. And another thing that we can do is stop the flow, and then the cell saturates with the gas easier because we are not removing the products of the reactions. So I think this answers the question. So yes, it is more difficult in the sense that we need to go to more extreme conditions. So it's not easy as it was before. Before it was too easy.
Gotcha. Yeah, you have to find that nice balance, right? You really don't want the bubbles there most of the time, but maybe once in a while you might want one for certain.
This is actually true, yes. Once in a while we actually want some bubble to take some measurements, yes.
Have you seen any, has your imaging resolution or sample prep, has your imaging resolution or sample preparation changed at all when using the new modified flow chips as compared to the conventional setup? Or are they just a direct?
So the preparation, I would say, is more or less the same. Maybe slightly easier, I would say, but I don't have, like, I think it's quite easy to close the cell. The problem might be there when we have the catalyst with big sizes, but that's the problem of both cells. So I would say the preparation is the same. The imaging, we don't have bubbles all the time there, so the resolution is worse, but we can produce them when we want. So I would say that it depends in which condition we put ourselves. And I believe we will obtain some good compromise, possibly when we will use the big chips with the spacer of 150 nanometers and not 500. So I'm quite confident also with this, that this will be a nice thing for the resolution.
Good. So it sounds like with the conventional or the standard setup, if you had liquid still in the cell and it hadn't de-wetted, and you've got liquid in the modified setup, your resolution between the two in those cases is comparable, right?
Yes, because actually the spacer and therefore the liquid thickness at the working electrode, so where the catalyst is there, is the same. It's not changed by the modification to the chip.
Perfect. Okay. There is a question which maybe we need to get back to Yifan here. He was asking, would it be possible to have the counter electrode to graphite carbon? And so I'm not sure if that's something, Kasia, you can answer or have experience with trying to change the electrode materials, but Yifan, maybe we can reach out to you and share with you some people and some papers of people who have deposited different materials on the other electrodes and such. Could you please comment on the improvement of the spatial resolution compared to the old non-modified chip? Thank you.
So we do not observe improvement of the resolution. We have the same, so if we're here, we are speaking about the resolution of the imaging, I believe. So we have possibly the same quality and resolution as in the standard configuration. So this is more about getting the electrolyte there to do catalysis more than improving the resolution.
Yeah, I think maybe he heard you mention the thinner electrochemistry chips might be better with the smaller spacer for resolution, and maybe that's where that question came from because he just entered it.
Yeah, this might be an nice thing, and then maybe we'll have the possibility to obtain, not maybe, it will be actually happening. We will have better images without producing the bubbles in the mouth. So during the experiment, when we are following the dynamical situation.
Exactly. And then I will do one more here, and then I think we are at time. The question is, have you tried to fully de-wet and do some EDX or eels and then re-wet the cell?
Yes, we did try to de-wet the cell, perform the characterization, and then it is possible to fill it again. So that's something that, yes, it is possible. So we did perform some EDX, not EELs, but basically it's possible.
Great. Okay, well, I'm going to wrap it here. And if there are any questions that didn't get answered, Kasia, I'll send you their questions and their contact information if you want to start a conversation.
Okay.
I think that's wonderful. And again, those new modified chips, we call them the flow management chips. And Kasia also alluded to the fact that we've got electrochemistry chips now with even thinner spacers to them to try and really hone in on that liquid cell thickness to try and improve resolution. So just reach out to us if you've got any questions, want to understand what we have available. That would be great. Kasia, thank you so much for the wonderful talk, for all the work that you did. The collaboration has been wonderful, and we look forward to seeing what additional results come from you in the future. Thank you so much.
Thank you very much, Jennifer. Thank you for your support, and thank you everybody for joining us and us today.
Yes, have a great day, evening.
And you too.
All right, bye.
Bye-bye.